let's start and maybe start recording as well. And okay, so we're going to talk about. Let me pull out the chat here. Yes. So we are going to talk about channel coding. No, not exam. Yeah, channel coding. I guess today, um, or like in general, like a channel today, like uh, kind of communication channel. So it's a little bit like okay, um, kind of related to communications. Like going back to communications. And so, by the way, my mic is working fine or what? Let me make sure. Sometimes Zoom just reset my. Okay, that's probably is okay. So okay, let of course I guess you all like most of you guys from ECE and then like communications is like a kind of like a required topic like so I assume like every of you like have went through some of these communication courses, telecommunication courses, and have some background on in that. And here, like if, from the perspective of information theory, um, we'll kind of like look at things in a higher level. So first of all, we will define a channel like as follow. So every channel you can think of is like just you have some input going into the channel, and then you have some output going out of the channel, right? So and in general, like everything else in this course, like we will assume things to be stochastic. So the input and the output in the channel, like you can think of those random variables. And so the channel is precisely defined by the conditional probability. Then like basically the conditional probability distribution of y given x. Given like a particular input of x, like what will be the output of y? And one thing that like people are interested in like will be how much information we can pass through this channel. And the theorem by Shannon, maybe I just kind of like jump ahead to give the result by Shannon, is that like he found that there's some kind of like channel capacity. Basically, that's saying that like if you are transmitting at a rate lower than that capacity, then you can ensure that you can find a scheme such that like lossless transmission of that message is possible, of those information is possible. If you're transmitting at a rate above the capacity, then there's no way you can find a scheme um, have like uh, that will allow lossless transmission. So so capacity like usually like kind of like for short like we just use C here to denote capacity. So channel capacity. So therefore like when the weight. So now I haven't defined the weight yet. So think of like weight like of course like the higher is like more information can pass through the channel. Basically the weight R like this is like weight. I use R for that like is the how fast you transmit through the channel. Mm. So now here like I didn't specify whether this channel is continuous or discrete, but you think of like this is at least discrete time. Like each time you use kind of like send an input, like take basically of this alphabet of X, you send something into the channel, and then at the other end of the channel you receive some Y out there. And so now let's define the weight. The weight would be like per each channel use. Uh, how much information you can pass through uh, the oh, okay. Let me rethink. Like, what should I define the weight? Oh. Weight, how fast is faster? Yeah. The weight, so therefore I should be like the number of bits. Oh, why I cannot write number of bits per channel use. So um for example, let's see. Let's say I have this like channel here, X and Y here. Now I'm going to have an encoder here. So this is an encoder, and then there's a decoder, and there's a message. I say M here. And this message, I say I can be like, just for simplicity, maybe just a number, and maybe like it's just a number from 0 to 2 to n out. You see why I want to use like 2 to n out. Like this is like so many numbers here. So I can like pick any of this number and transmute. And then like this number will be kind of go through this encoder, and then the encoder will send out some signal to the channel, and then channel pass through this. I mean, into the channel, and then the channel other end of the channel, you get the Y here. And earlier here, I'm assuming like each time I just send, I mean, each message is modulated to just one channel use. I mean, just one character, in the sense like this is just one character here. But in general, like I can have like each of message to kind of like modulate into like n uh, input characters here. So then in the sense like, for example, like if I have message m here, or like if my message is 1 here, what I'm transmitting into the channel will be like some xm1. So like this is like, you can think of this as a code word like of message 1 here. And then if I have 2, I will send an x and 2 and so on. Like, and I have like the number of messages here, let's say it's 2 to n out. Then I have like xn like 2 to n out here. So I hope that's clear. So xn here would be like, so this for example will be like just x1, sorry, let's see. It's a vector, right? x1 1, x2 1, and so on, like xn 1, something like. It's just a sequence of the kind of like characters, like of the characters of x, and then I will send through the channel. And then at the other end, I will receive like y1 up to yn, right? Something like that. And then from there, like I try to decode that. Like I try to look at this y1. I will have a decoder. Let's say I call it this decoder, maybe just D here. Decode this. Hopefully, I should get back like some 1 here if I'm transmitting 1, or like maybe this I get m hat here. And I hope like this m hat will be equal to the original m. So now I hope it's clear now why I pick like the number of messages is 2 to n out. So let's see why I want to do that. Because like, if I pick that, then the weight will be out. Because like you think of like what should be the weight defined will be like how many bits I can transfer uh, through the channel per channel use, right? So the number of bits here will be like 2 to n out log 2 to the n out, right? For a message of length m. Um, and that would be like just n bits, n out bits here. And then since I have used like n channel use, so it's like the weight. So you see the weight will be like 2 to n out log 2 to the n out over n, right? So it's like n out over n is basically it's just out here. So so far so good, right? So okay, this is basically our setup. So this is like our abstract setup of channel. So and then like the question is like how much we can transmit through this channel. Of course, this channel will be depends on like, how much I can transmit will be completely characterized by the channel statistic. This is basically the conditional um, probability distribution Py given x. And also like we'll assume the channel is memoryless. So so you often hear about like people say memoryless channel. So memoryless in the sense that like okay, if I have like a p y as a sequence given x here, maybe I want more precisely, maybe like a factor of like yn given xn here. So in general, I can use chain rule. It will be like y1 given xn, right? And py2 given xn y1 and py3 given xn. Uh, sorry, this is y1 and this is a xn y1 y2 and so on so far up to like p yn given xn ynsa. Now this is like just base rule. This is nothing, just base rule. But if my channel is memoryless, then your y, like the output y here, it will only depends on nothing but the current input. So in the sense that you have y1 here, it shouldn't depend on, okay, basically it won't depend on the future input. It only depends on the current input. So this one will be just equal to y1 x1. Okay, I just give a pause here to see if you guys are following. So what is this precisely? How can I simplify this? This, the first one I say like this, it will be just y1 given x1. How about this one? Yes, actually, it will only depend on the current input. So you have like py2. Of course, it will only okay. Given the input, like you don't care about the previous time output, so you only depend on xn. But it also won't depend on other inputs. Like, I mean, the inputs at other time instance. So only will also just equal to py2 given x2. So we can ultimately simplify to something like that. So all of these terms will be similar to that. So eventually I will just a product of this pyi given xi, something like I equal to 1 to n. Um, and so I mean, of course, the channel will depend on the conditional probability, but because of the channel is memoryless, it will only depends on the marginal conditional probability of like the the probability of current output given the current input. So like this. So we specify the entire channel. Now, as I said, like, okay, we have this capacity, like Shannon's film have kind of like, I just want to add a remark here. Now you're looking it back, it doesn't look like something like really spectacular. I don't know what do you think about that. But in the times like when Shannon introduced that, like um lots of people find this result pretty surprising because like this is still in the age like I guess like in the transition from like analog to digital age. So people like think of stuff in an analog way. So they have like analog channel, they transmit signal in like everything is in analog. So to them, like it seems like it's impossible to transmit signal error free. So when you transmit analog signal, you also always have some noise. It doesn't look like you have any ways that you can get away with those noise. And but if you have digital signal, it's another story. You can introduce some channel code and so actually, after Shannon's like this theorem, like that has a whole field like channel coding. People just study the channel codes. Like, until late 90s is a pretty active research area, and then there's LDPC codes, and more or less the area kind of died down quite a bit. Like it looks like it went to, I mean, pretty much close to the theoretical limit. Like even though that's polar cold like several years ago, like but I guess the impact like now I don't think like channel coding is a very active research area, but uh, historically speaking, it's important. Um, and so now I talk about this capacity, but I said like I jump ahead. I like to jump ahead to give the capacity, but I didn't. I forgot. So the capacity, actually, you may guess like what will be the capacity. It turns out the the s- the answer there is like pretty intuitive. So you think of like how much information you can transmit through this channel will be, you just think of like how much information are overlapping between these two, between the input and output, right? So then I guess it probably won't be too surprising, oops, to find that like this, the channel capacity will be something like the mutual information between X and Y, basically like how much information is shared. Maybe I use a different color. This is like kind of the key things here. The capacity um, is IXY, but know that like you have some freedom to pick the input distribution, right? So for different input distribution, you expect the mutual information between X and Y can be different. So therefore, like, the capacity will be really trying to maximize, or like sometimes people write supremum or something, but I would just write maximum, uh, like supremum in the sense that maybe you don't have the maximum and so on, like all these kind of like mathematical analysis kind of complications. But yeah, it doesn't matter. Like maybe we just write maximum uh, px, something like that. So you're trying to now find the uh, maximum mutual information between x and y uh, with respect to the input distribution. You have the freedom to pick what is the input distribution. I'm trying to pick the one that is going to maximize this mutual information. We will show that at least um, I guess I won't spend time to uh, give the entire forward converse proof. I used to do that, but I guess um, probably I want to like kind of reserve time for some other topics. So, but at least I will give a forward proof, just showing that like or like kind of like a overview of the forward proof uh, to show that like as long as your weight is less than this, less than the capacity, you'll be able to find a code such that like you can transmit the message uh, losslessly. In terms of the proof is like uh, really neat because it's like some of this really amazing proof because like the proof is non-constructive. It's using some random coding argument. So if you think of like, okay, if I have some problems like this, it just doesn't look like there's um it looks like this is very difficult problem to come up with a proof because like you can have like all kinds of this distribution here, right? And and the problem is extremely general. And how can I consider all the combination? Like the straightforward like if idea would be simply okay, like whenever I have like a distribution, I'm trying to see like what will be um, some kind of code that will achieve the capacity, and I will show that uh, that code achieving the capacity, and that the transmission rate is indeed, or like the want to find the code that can transmit as much as possible. And I want to show that the weight for that code is actually achieving the capacity, right? This will be really kind of like, I guess, like first idea people maybe will try to approach this problem. But Shannon is really ingenious idea. It's like he find that he doesn't need to think along this way. He doesn't even need to think about whether the code is optimum or not. So he used some random coding argument. He like create a random code and then show that like just using that random code, he can achieve the capacity. And then it's a we have a converse proof. I'm showing that like you cannot get beyond the capacity, but the converse proof I probably will leave it. If you guys are interested, it's on the notes and you can read it yourself. And basically, it's just using the same similar things uh, we show the converse proof for the source coding theorem, like the Fano's inequality. Um, so, but before I continue to talk about the forward proof, let's give some example. Um, so the simplest example would be like a so like binary symmetric channel. This is probably the simplest like discrete memoryless channel you can imagine. So I have um the input here, like okay, like p y given x here. The input here is binary, so it's like 0 and 1. The output is also binary, also 0 and 1. And like it's symmetric channel in the sense that the of course like if you send out, like for example, if you send out 0, like x is 0, if your y is always equal to 0, then there will be no error at all, right? Like and if like what I mean is like if you send out, okay, let me put this way. If I send out x equal to 0, then I y equal to 0, and if I send out x equal to 1, y equal to 1, if I for sure have that, then there will be no noise at all, no loss at all. And oh, okay, by the way, just a fun question, like uh, capacity, oh, is lossless channel. So do you know what is the capacity? Okay, I just give a kind of like dummy setup that like, so let's say like if I have this binary channel here, in the sense like channel here, that whenever I send out 0, then I receive 0. If I send out 1, I receive 1. I always receive 1. So what will be the capacity of this channel? Wait, wait, capacity. Okay, remember capacity is what capacity. Um, you can think of capacity as the amount of information you can send through the channel, and the amount, of course, is very vague. Amount in the sense that per each channel use, each time you use the channel, how much information you can send through this channel. Hmm. Yeah. It should be 1 bit, right? So, um, so that's like two outcomes, but there's 1 bit, right? Um, so because each time you use it, you the input, like basically the input alphabet size, force you can only send, I mean also the output, yeah, both input and output alphabet size, I kind of like restrict you to can only send 1 bit each time, right? This is a dummy channel. Is like each time you use it, it can send 1 bit. So if there's some error, you will expect that the capacity will be smaller, right? Okay, give a second example now. What if like whenever I send out 0, I have y equal to 1, and if whenever I send out 1, I have y equal to 0. So what will be the capacity then for this channel? Yeah, that's very good. Yeah. Yeah, I guess you kind of like came across this before. Like this supposed to be a little bit tricky question. So um so uh the live answer can be zero or something like someone like totally kind of unaware of this trick is like, okay, it looks like you have like some error here, like this is like 100% incorrect. But know that like when you're 100% incorrect, it means that like you flip the answer, you're 100% correct. So and like if if you have situation like that, you can always recover x, right? So when you have y equal to 1, you know x is actually 0, and y equal to 0, x is equal to 1. So now the general case will be like I have y, yeah. So general case will be y is equal to, let's say, how do I write it? X, maybe I put a log x, like since I mentioned a log k here. So, okay, I don't know whether you use a notation like that, like I used to use, I don't know what other notation you use. So this is just log x. So like if I 0, it become 1, 1 is equal to 0. So y is equal to x with a probability, okay, maybe like this. A probability 1 minus p. This is like with, oh, good. And then and this side with probability p, basically. So in this case, what will be the capacity then? So this is something so we are interested in. I hope it's clear. And know that like from the argument here, you see that like um, I have the channel capacity, let's say the capacity as a function of this p here. This is called the what do we call that? Like um, anyone can help me? Like what do we call that? Like I can't forgot. Um, let's see if I write it down here, like somewhere. Yeah, crossover probability. Yes, yes. Crossover probability. So we can kind of like evaluate the capacity kind of with respect to the crossover probability. Note that like from the argument here, we know that like Cp is equal to C minus 1 minus P, right? So if I have the error is like, for example, it's like C.1 should be just equal to C.9, something like that. And we can focus on probability P, like this crossover probability is less than 0.5. For the case less than or equal to 0.5, let's say. Now let's try to compute the capacity here. So capacity is equal to maximum. I have this px here, ixy, right? And let's see, like I can write ixy as hy minus hy given x. um, let me yeah, let me elaborate a bit more. I'm thinking if I can. I'm thinking whether you already see it or maybe if not, maybe okay. Let me just continue first. So I can expand this. Like I hope you guys are kind of like okay. That's good. uh, at least I'm not wasting your time then. Um, hy given x equal to 0. Px equal to 0. Okay, but hopefully you will find these steps not too confusing, like because you guys have like midterm next week, like you better be ready like to if you find any of this confusing, just stop me because like yeah, that um yeah, that you can save quite a lot of time revising the material yourself. Yeah. So and then I okay, let's just pick any of these. So what is a hy given x equal to 0? mm, mm, yeah. Missing a term, I guess. Yeah. Hmm. Or maybe you can think of like what's py given x equal to 0. So this is like some kind of distribution. Right? Why can I take two different values here, right? Y equal to 0, y equal to 1. So this is essentially just a very simple distribution. This is like y equal to 0, y equal to 1, right? And this is like py given x equal to 0. So when x equal to 0, y equal to 0, that the probability is like 1 minus p, right? So I have this is like 1 minus p here. And when x equal to 0, y equal to 1, I have like p here. So the distribution it will be just like that, right? And then therefore like hy given x equal to 0 is just equal to h of this distribution, right? And h of this distribution will be, yeah, we can have this shorthand notation again. It's just hp. I guess I mentioned it once. That is essentially just like minus p log p minus 1 minus p log 1 minus p. So and I guess it's obvious that like so this is a hp, this one is a hp as well, right? So and then like therefore it will be just what maximum h. I guess I can erase this now. Hy px minus hp px equal to 0 plus px equal to 1. So what's this? What's this? Yes, that's simply one way. So then okay, then you see like okay, this is like trying to maximize um, px hy minus hp. So what's the maximum of this then? So maximum of this, okay, first I need to consider, so this is like does not depend on like px, right? So px is base like p itself is like a parameter of the channel, right? The channel parameter. So hp itself is fixed. It doesn't depend on the input distribution. Um, and so only this can be affected by the input distribution, right? So what is the maximum hy um, here? Okay, uh yes, that's a actually uh that's a bad choice of questions from myself. So both of them have the same answer. Now I got confused like which one you are answering. So yes, this will be one way. Um, so I yeah. So yes, uh, you see, okay, look at the setup again. Like I have like some x here, like this is a x out of this distribution px here, and then I go for this py given x, and then I have this py here, right? This y here, and this y given x is just this binary symmetric channel. Now you see that like if I have the x, um, oh, okay, I guess maybe I've lived, yes, uh, but okay, let me ask one more question. Like, so what should be hpx to get hy equal to 1? I need to pick px. So yeah, you're right. Like the maximum may be 1, right? So but which px will allow me to get like hy equal to 1? Yeah, yeah, you can yes. Or you can describe it. Yeah. Mm, uh, hmm. Yeah. HP. Okay, P is given by the problem here. You cannot change it. P is given by the. I mean, yeah. I mean the parameter P here is like given by the problem. Yeah, maybe I should use Q earlier so that. Yeah, yeah. But it's okay. Let me keep. Um, yes, yes. When you have like uniform, so know that like okay, what's Py equal to? Okay, wait a sec. Py equal to 0. The probability y equal to 0 is a let's see p x 0. So that is like when x is equal to 0, and then it's not going to change, right? 1 minus p, right? Per se, um, the probability of x is equal to 1 times p, right? So if I want to get like hy is equal to 1, I want to have the distribution to be uniform. Therefore, like py equal to 0 should be equal to py equal to 1 equal to 0 0.5, right? And then I And then in this case, so how I can get this is equal to 0.5 will be simply like these two are 0.5, right? So this is 0.5, then this is a 1 minus px0 is actually also 0.5. Then 0.5, 1 minus p plus a 0.5 p will be just equal to 0.5, right? So if your so in some way, if your input is uniform, then your output will be uniform as well. So therefore, your hy will be just equal to 1. Then you'll be getting maximum, um, basically ixy. So therefore, the capacity. So therefore, maybe I erase this one now. So for binary symmetric channel, capacity is just like 1 minus HP. So it's okay, right? So let's give another example. So Gaussian channel, maybe just more precise, additive white Gaussian channel. Actually, just additive Gaussian channel, I guess it's okay. So I will simply have, let's say, the input now will be something continuous. So I have like x is continuous. It's just a real number, and y is also continuous. It's another real number, and my py given x will be defined as a something like y will be equal to x plus z, where z is just a Gaussian kind of like random variable. So for this case, we, we, we still have the same like channel capacity formula. So the capacity is still like ixy. So even though like here, honestly, like we kind of like I would say hand wavy a little bit, because like earlier like we consider discrete channel, now like we getting something is continuous, but the input and output are continuous. But remember that like you have the how what should I say, you have like differential entropy. Remember, like you have differential entropy is related to like discrete entropy as like, maybe I put it other way one. If you have like a um kind of like continuous random variable, if I'm going to discretize that like with some quantization step size, then remember that we have something like that way, minus log uh, delta, something like that. And know that like if I consider, for example, mutual information between x and y, they are continuous. We can consider like some very very tiny like quantizer to the input. Like for example, like this, I can consider this as a the defined as a, okay, this is a hand wavy as a ix delta y delta have delta goes to 0. Take the limit of that and know that like this guy here, I can expand as a hx minus yeah, I'm okay. I'm thinking like maybe I'm taking a hole myself. Let's see. Wait a sec. I have yeah, what I want to say like this is a good argument that like this will be uh um, hmm, maybe let me continue to write it down first. A log delta, this is a h x given y minus log delta. So I would say that the log delta cancel. So okay, like this is like what I'm saying, like why this is like okay, like to do that, because like if you look at these guys here, like if I actually I'm not writing this equal first, like if I just think of like if I quantize something, like if I have x and y here, um, like between two variables x and y here, and I look at the mutual information of x and y, and now they are continuous. But I can think of like, okay, let's see, like I trying to consider the case, like trying to discretize that to get like x delta and y delta. Then I think like, okay, I x delta, like I y delta should be a good approximate of like I x y somehow. And I x delta and I y delta. So what will that be? Will be just like hx minus log delta minus hx given y minus log delta, and they got cancelled. We really will just get back like ixy. Um, so okay, it doesn't matter. I guess I probably confuse you more than like contributing something extra. So just trust my word that like okay, I'm even though like we go a step like from discrete to continuous. And of course, even for the discrete channel, we didn't show it yet. But what I'm saying, like the expression will be the same, like for this guy, even like for continuous case. Yeah, you can still think of like for a continuous channel, the capacity will be still. Uh, oh, sorry, like delta. Yeah, x delta is like the um, sample for x with quantization step size. So it's like x with a quantizer with step size delta. For example, like my delta is like 0.1, my x is continuous, maybe 0.9.1, 2, 3, 4, something like that. So after the quantization, I got 9.1, something like that. So now, because after the quantization, this is something discrete, right? So then I can talk about the classical discrete canonical entropy rather than the differential entropy. and and also like we can think of the capacity, because now but for this one I can okay since you asked the question, let me just repeat the whole thing again. I think I got it, like I forgot, like so what I argue is that like um of course I okay something is like fishy is like because I didn't show that the capacity um of the channel is given by that expression. I'm going to show that, but my proof is only restrict to like discrete random variable. So I will only restrict myself to discrete random variable. But I want to say like this is applicable to continuous random variable, because like you can always think of like if you have channel is continuous, so I can always like discretize the input and output, right? So I can discretize that. So I have like y delta and x delta, and I can make this quantization steps are arbitrarily small, like it doesn't matter, arbitrarily small. But as long as it's discretized, then the capacity of this channel will be ix delta, y delta, right? So because I now it's a discrete channel, assuming I gave the proof, I'm sorry, I didn't yet. If I gave the proof, I know the capacity is just this one, right? Now, um, what or like maybe just forgot the px here, just will be like this one, right? The how much information I can pass through will be like the mutual information between x delta and y delta. Uh, now, but if you look at what's I x delta and y delta is just equal to h x sorry h x delta minus h x delta given y delta, um, and this will be just a hx minus log delta approximately, and this is a minus h x given y delta. minus not delta. But this is like approximately hx given y as well, because if you are sufficiently fine quantizer, knowing y delta is the same as knowing y. It doesn't, it's the same. And then you have log delta cancel, that will give you back just ixy here. So therefore, like the capacity of the channel will be just ixy here. And ixy is just in this case, even ISY will be really you look at the notation here, actually you don't know whether this is a continuous and discrete random variable. And actually another remark here that you may wonder, like, okay, why when we deal with like continuous random variable, the differential entropy we should have like small letter to represent the differential entropy, but for discrete sorry for mutual information, even for continuous random variable, we have ixy here. Because ixy, like whenever is we are considering mutual information, it doesn't matter, it's like discrete and continuous. Uh, the the expression is eventually the same. As you can see, like if I take the limit or conversion, I kind of like trying to discretize that like x and y with arbitrary, like of course I need to like with sufficiently fine quantization, then this one will be just the same ix delta y delta. So therefore, like you don't see people use a notation like ixy something like that, because they are essentially the same. Like yeah, but for entropy they are not, right? If you have like something is have a continuous random variable, if you discretize that to x delta, so this thing is not, so this thing is not the same as like hx delta. So you need different notations for that. So okay, it's a bit of digression. So but um, the conclusion is just that you don't need to worry about um, um, that our proof. If you are really someone is like go down to detail, then you you see that like, okay, why skip the proof like about continuous random variable, even though like when we talk about the channel coding theorem, um, we are only dealing with like discrete channel. Though, so how do I know that like this will can apply also to continuous channel? But if you look at that, this is like actually pretty reasonable. And also like you see like that's something like quite um in the sense that mutual information is like quite a bit more like prettier than entropy in some sense. Like um I came across, but I don't know which one now. Like they were textbook like at the beginning of this field, like information theory, they start defining everything like using mutual information rather than like conditional, rather than using entropy. Um, yeah, but I don't know, that is like probably like more attractive to mathematicians, because like it's it looks much more much prettier. But I guess for intuitive like understanding, still I think like entropy is easier to understand than like mutual information. So, but anyway, like I have quite a bit of digression here. So, but okay, let's go back to this question here. So I have a continuous channel, Gaussian channel, that with an input x, then the output will be y equal to x plus z, where z is just additive Gaussian noise. So with a variance sigma square. So okay, the capacity, same formula will be this guy. So then will be like hx. Let's see, I can kind of do it similar to like what we did earlier for binary symmetric channel. So I can write hy given x, something like that. Now then I can write like maximum px hy minus y is equal to x plus c or x plus c given x. Hmm. Now, given x here, you see that like x become a constant, right? Because you're given x, then x is essentially just something a constant. It's deterministic now. It's not something. Yes. Just know that like when I when we write hy, y kind of like implicitly we are implying that like y is continuous, and when we write x, let's say like x is discrete. So therefore, like even though it's like actually, if you look at the expression, you can both of them write like this, like p y, and this is expansion minus not p x here. So, but if you continue to expand this will be a summation, right? But this will be an integration. So because like now px is a PDF here, probability density function. So it should be the expectation is like minus log px px. Okay, maybe I write it the other way is better. Px log px dx, something like that, right? But here, on the other hand, this will be a summation y minus py. Log. Oh, okay. I'm so sorry. Yeah. Yeah. Thank you for catching me. Yeah. X. Py dy. Okay, I need to erase this dx here. Yes. No, I need more coffee actually. I woke up kind of early today, like 7 a.m. Yeah, I usually has a light out. I slept like 2 a.m. last night. Yeah, I'm not good with like 5 hours sleep. Yeah. So I have my coffee, but it doesn't work. Yeah. So thank you. So yeah, okay. I hope it's clear. So because I here is continuous, so we should use the notation small h here. So now okay, we were here. So uh given x here, so that means that x now is considered deterministic. At least I in in terms of like what we are considering here, like x plus z. So therefore, like this is really equal to h z given x. I hope this is. I hope this makes sense to you. So think of like whenever I have like h x, let's say should be just equal to h x plus some constant. If I shift that variable, it shouldn't change the entropy, right? Because the entropy is just depends on the spread. So how the distribution look like. If you shift that distribution, or even though like okay, I didn't draw it nicely. So if the distribution of the same shape, then the entropy shouldn't change. So okay, so therefore like okay, I have like hy minus hz given x here. Now I can look at this one here. Hz given x, what is that? Where is that? So Z is a noise applying to the channel, right? So there's no reason to believe that the noise here will depend, I mean, somehow will depend on the input, right? So when you have a channel, it's hard to say, but often the assumption is like you put in different input, the noise should be something independent. It shouldn't be like the input will depend on what kind of like signal you're sending into the channel. So it's a good assumption that like this should be just these two x and c should be independent. So this therefore like it will be just equal to hz. So it will be hy minus hc. Um, something like that, right? Um, Now we boil down to something pretty similar as before in the case of BSC. Um, so we have the second term here, HZ. So Z does not depend on the input. So it doesn't depend on the input distribution PX here. And HZ, by the way, is, if you remember the formula, is just 1/2 2 pi log 2 pi E sigma square. So this is HZ here. So the second term is just this one. It's just this one here. Now the only question is, say, what PX we should pick to maximize HY. So here, there's something you will see, like we have some problem here for the original problem. Like we set up this problem originally. If I didn't put in any constraint on X here, then I can make this HY unbounded, right? Because um think of like X is a like any signal, like the signal that with like infinite power, then Y will have infinite power as well. So when what we mean by infinite power will be like you have the Y can spread to infinity, right? And remember that, like uh, for example, if you have a continuous signal, if sorry, like uniform signal, um, uniform distribution, and remember, like if I have like uniform distribution, something like with this, let's say, if a width of d, this is 1 minus d, let's say, then the entropy is simply is equal to log d, right? I believe. So therefore, like if you continue to spread, actually you can get the entropy like to be unbounded to get to infinity. So this means that like this will be a not a well-defined problem, because the solution will be infinity if we allow x to be unconstrained. So, but of course, in reality, like we are not interested in the input that is unconstrained. We have this very natural constraint. Will be like we would like the power of the input to be bounded somehow. Eh? So let's say, let me introduce another constraint that like the expectation of x squared, that's basically the power, is like bounded by big P here, by the power. So this is like some kind of input power. So we need that again. We need that because if we don't have this constraint, then this problem, the solution of this problem will be kind of unbounded. Then like this is meaningless to us. Like what's the capacity? Because the capacity is basically infinite. So now with this additional constraint, let's say the power is like less than P. What will be the maximum HY? So maybe I just ask you, like, what is the if okay, let me, maybe I recall you something, um remind you something. So we call that, like, I have if the variance of Y is given by sigma Y square. So what was the maximum HY? Do you remember? There's a question for that. What's the maximum hy when the variance of y sigma y square? Yes. I need that to be normal. And how about the expression? But it's on here, right? The expression is here. Yes, the expression is here. Um, so when I have basically, if my variance is like sigma y square, I can get maximum entropy to be like 1/2 log 2 pi e sigma y square, right? If y is Gaussian somehow, right? Now see if I can make y to be Gaussian. I can, right? What I can do is I know C is like Gaussian, right? Independent Gaussian. If X is also independent Gaussian, I don't know, maybe like you don't know this, but yeah, if you have taken probability, you can try that like at home or something like that. If like X am Gaussian, Y am Gaussian, X plus Y with X plus C is Gaussian. What is it to be zero? What to be zero? Uh, you mean zero mean? Oh yeah. We will probably like to make a zero mean actually, because you if okay or like X to be zero mean So basically, if like X is zero mean, so if X is zero mean somehow, if X is zero mean Gaussian, let's say if I pick like X to be zero mean Gaussian, then the variance of X will be okay. Variance of Y, so okay. Then Y is basically um will be just also Gaussian with variance P and sigma Y square per sigma Y square. So I hope this makes sense to you. So because I think of like what is variance in this case, like everything is zero means. So we make everything zero means, it becomes very simple. Because when everything is zero means, so variance of y is just equal to expectation y square, right? So equal to expectation x plus z square, something like. And then I have like expectation x square plus expectation z square plus expectation x z plus 2xc, something like that. I know that like xc are independent, right? So xc independent. So okay, this is one thing very important. Like when something is independent, I should have just independent zero mean. Yeah. So no, independent is okay. So when it's independent, then you can very easy to show that this is equal to expectation x, expectation c. Um, actually, side note is that like uh, this is a condition to be uncorrelated, but independent will imply uncorrelatedness. So, but if you have this satisfy alone, but like you don't have like pxc is equal to pxpc, then you say that the variables are uncorrelated, but not independent. Um, so, but if it's independent, it will imply this, and so this will be equal to expectation x, expectation c. So they have zero mean, so this term will be gone. So this will be just variance of x plus variance of c, right? So okay. But actually, in general, like if you have like two random variable to be independent, like the variance of the sum of the variance of the sum of the variables will be just equal to um, sum of the variances. Um, so, but yeah. So, okay. So then, yeah, then that's it. Actually, you can, okay, you can easily verify that this is indeed the maximum that you can get. So this should be the maximum you can get. So therefore, this will be maximum px. Now I have, yeah, I better maybe erase this one. This will be like log 1/2 log 2 pi e 2 pi e sigma y square. Oh, sorry, like this is like p plus um yeah, p plus sigma square. Yeah, I'm sorry. P plus sigma square. This is like the variance of c is like sigma square. Yeah. So it's 2 pi e p plus sigma square minus 1/2 log 2 pi e sigma square. And so this, yeah, I can erase this at the maximum is gone. So it's equal to 1/2 log p plus sigma square over sigma square. Yeah. And and equal to 1/2 log 1 plus p over sigma square. And note that this is nothing but just the signal to noise ratio. So it's like 1/2 log 1 plus SNR. Um, yeah. So any questions here? So it's yeah, I think like here I'm not very organized. Let's see if I yeah, actually I can fill in some step to make it maybe a bit better to digest. Is I can prepare px here. Hy is maximized when I have like the entropy is 1/2, basically when like y is Gaussian, right? When y is like Gaussian, I have 1/2 log 2 pi e sigma y square, the variance of y, minus 1/2 log 2 pi e sigma square. Now, given I have also the constraint like sigma x square is less than equal to p, and this is just equal to sigma, wait a sec, maybe I should write like variance of x plus sigma square. So this is always true. Basically, um, here sigma y square is the variance of y. Variance of y is always equal to variance of x plus like variance of the noise when the noise and the input are independent. So this is always true, always true. Now, I will get maximum variance of x when x is zero mean. When x is zero mean, variance of x will be just equal to p. So that will give me this one here essentially. So if you don't have zero mean, then like your variance needs to be smaller because say for example, if you consider you have x here, um, um, let's say this is a what should I say, like how do I how do I draw it? Let's say I have the x value here, like split. Um, maybe I just use the this axis is time. Let's say like I have x cap varying, like right. This is a x varying. If it's zero mean, it would be something like that, right? And the power will be like, okay, this will be the power, right? So if let's say if I have some shift here, like let's say I have like instead of like my mean is here, I've mean is somewhere else, like maybe somewhere here, the mean is here, then I cannot fluctuate as much. Actually, I cannot fluctuate at all, right? To get the same power. So therefore the variance will be smaller. Oh, okay, okay. Anyway, like I guess like hopefully it's not mm, yeah, okay. So I'm feeling that the deeper I get to this, like I dig a bigger hole, but I guess you can just look back to here, like this should be fine. Yeah. Yeah. So okay, I guess I will just pause here for a bit, like have a break. Again, like 15-minute break, and then like afterward, like I will just continue and see like if the speaker is here, then we will have like the last presentation. Yeah. Cool. So I guess we'll just break for 15 minutes again. We'll come back like 4:43, I guess. Yeah. Okay. Thank you. Okay, I guess I will just resume. Like during the break, I kind of like try to smooth the kind of like the proof for the Gaussian channel, the capacity of the Gaussian channel a little bit. Um, and I guess okay, I will just quickly go through it again because I think I didn't articulate really well earlier. So we ended here. I guess this is quite obvious, right? So the first couple steps is very similar to BSC. So we just expand IXY like into like HY given X instead, HY minus HY given X instead. And then like Y is equal to X plus C, and because like uh given X, like X is a constant, so this is like equal to H Z given X. And then C and X supposed to be independent, the noise shouldn't depend on the input, then this will be just equal to HZ. So here, I guess I got messed up quite a bit, like in the sense like I don't think I articulated well. So then afterward, like you think of like what's the measurement? Of course, like HC here doesn't depend on the input distribution anymore. So it'll be just equal to one half log 2 pi e sigma square. But HY, you think of like what's the maximum HY? So I don't care like what what um what precisely the distribution yet, but let's say if I'm given the variance of X, then the variance of Y, because like Y is independent, sorry, like X is independent of C, we always have variance of Y is equal to variance of like X plus C is equal to variance of X plus variance of C, right? So the variance of Y will be just equal to variance of X plus variance of C. So this one is equal to sigma square. and for this variance, the distribution has the highest entropy will be just Gaussian, right? Will be just equal to, therefore equal to one half log 2 pi e sigma x, variance of x plus sigma square. And now variance of x, and by the way, this is achievable. This one is achievable when x is like is not Gaussian, right? Because when x is Gaussian and z is also Gaussian, then when you have like two independent Gaussian added together, it's still Gaussian. So you can refer back to uh, your probability course, or like you can just actually write it down yourself. If you have two um, Gaussian random variable, add them together, they are independent, they should get a Gaussian random variable. So therefore, like this inequality is also achievable. So achievable when x is Gaussian. Now then like, but the variance of C here is equal to expectation x squared minus x bar squared. So this is just some of this really common formula you should use, it should be on top of your head. And then like now, so therefore like if I have um x is zero mean, then this will be gone, right? So then this will be maximized, right? So because I have a constraint that like x squared is less than equal to p. I want this guy to be big. I would like x bar to be equal to zero. In other words, x to be zero mean, and the maximum expectation x squared like I can get is basically p, right? So therefore, like this will be less than equal to p per sigma square, and this is achievable basically when x is a Gaussian to be zero mean and variance is equal to p. So therefore, the first term is just this one, and then you will get like one half log p per sigma square over sigma square. So this will be just 1 plus p as p over sigma square is just the signal to noise ratio. Mm, yeah. So I hope this is much clearer. And and by the way, for band channel, I guess that's the formula you all seen before. For band channel, uh, addictive white Gaussian channel, white Gaussian noise channel. um, let's say the bandwidth of W, uh, the two side noise spectrum is say N2 NC over 2, let's say, then you know that there's a formula from your communication theorem. I guess like the capacity is given by like W log 1 plus P over W n log, something like that. Now we can show this one now, knowing I guess you saw this formula before, but you never know where this formulas came from. But um, this formula is simply came from like what we had like in the earlier slide. So know that like for each Gaussian channel, the capacity is just a 1/2 log 1 plus SNR. Now think of like when you have a band limiter channel, like so uh, for a band limiter channel with like bandwidth W, uh, well, by the way, like what's the like quest do you still remember like the uh like quest kind of like channel like quest theorem when you have a band limiter channel with like bandwidth W? Actually, I think it's usually framed in another way. It's like if you have a signal of bandwidth W, how many samples, um, what will be the sampling rate? Mm, uh, channel request. I don't know how they call it. Channel request film. I guess something like. Um, maybe like you guys do you still remember what is the sampling rate for perfect reconstruction? Yeah, yeah. I guess you're correct. So when you when your signal bandwidth is W, the sampling rate is twice, right? It's like 2W, right? And actually, the other way to think of that, if you have the signal here, you have the sampling rate to be 2W such that like you can cover a signal of bandwidth W. It means that like, okay, this is a brain twister like to me. Like always I can't really need to think a lot about this one. It means that like if you have a band limiter signal with like bandwidth W, uh, the degree of freedom, uh, this degree of freedom of a band limited signal is 2W. Does it make sense? Right? Does it make sense to you? So um, you think of that like, okay, you need to get perfect reconstruction. You need to have 2W samples here. So without 2W samples, you don't get perfect reconstruction. So in other words, like, if you have a signal, the bandwidth is W, you cannot have the degree of freedom more than 2W, or like your degree of freedom should be like just 2W, because like if more than um if you have more than 2W samples here, um, you will get a signal with bandwidth like is beyond that W limited signal. Okay, that probably is like the hardest part, at least for me. So, but I guess like the more you look at that, the more you find that okay, it seems like makes sense. It sounds reasonable. And if you accept this, then like everything is like very okay. Afterwards, like very simple. Like then for band emitter channel with like W sample, and if like the noise there is all like analog over two, then you can think of this as just a 2W parallel channel. So you have like 2W parallel channel, and the signal to noise ratio there is just equal to um, P over uh, 2W times N naught over 2. So therefore it's a P over W times N naught. So I have 2W of this kind of channel. So therefore the capacity is 2W times 1 half log 1 plus SNR. So 1 half got cancelled. So it's W log 1 plus P over W N naught. So this is basically how we get this formula that you all, I assume that all of you seen this before, like in one of your communication class. So okay, I see that Richard is here. I guess I will just make him co-host. I think it's a good time to pause here. Maybe I'll let him to. Richard, you are here, right?
Yeah, can you hear me?
Yes. I guess I will just let you to present first, and then I will come back for more materials here.
Okay.
Yeah.